Okay, we're going to look at solving exponential equations by using the same base. So when working with exponential equations, it's really important that you know a couple of facts to start. One is you got to know your powers. So know your powers of 2, and you can always generate them just by multiplying over and over by 2. So remember, anything that's raised to the 0 power is equal to 1. 2 to the first is 2. Multiply by 2, again I get 4. Multiply by 2, again I get 8. 2 to the 4th is 16. And you should probably know this out to at least 2 to the 6th. But if you're not sure, you can always kind of like factor it and see what you have. But you want to be able to rewrite something that starts off like, say, with 64 and be able to rewrite that as 2 to the 6th. My powers of 3, again, 3 to the 0 is going to be 1. And you should at least know your powers of 3 up to 3 to the 4th. You may not recognize the 243, but I can tell that is divisible by 3 if you add up the digits. I have 2 plus 4 plus 3, that's 6 plus 3 is 9. 9 is divisible by 3, so I know 3 goes into it. So you could divide and then realize, oh, I got 81. So I already know that was 3 to the 4th, and that's how you can figure out that one was 3 to the 5th. Next most common one we'll be using the powers of 5, and should go no powers of 5 out to at least 5 cubed, which would be 125. And if I multiply that by 5, I get 625. And then a couple other ones that you may come across. Certainly you need to know your squares. Powers of 6. I didn't bother with powers of 4 because powers of 4 are just powers of 2. So we can just do it as a base of 2. So certainly recognize 6 squared. You may not recognize 6 cubed, but you can see it maybe on homework problems. Powers of 7. So same kinds of ideas. At least know it to 7 squared. Probably won't know 7 cubed. Probably won't come across that one though. And then the other one that comes up, because powers of 8 are still powers of 2. Powers of 9 are powers of 3. Powers of 10 though, those ones are kind of unique and those ones are kind of important. Well, certainly powers of 10, just going with positive numbers, are easy to recognize. Because for every exponent we have, kind of tells me how many zeros to put after the 1. But also we're going to be working with negative exponents. Now, with most of these ones, when we use negative exponents, we're just going to get 1 over the same number. We're going to look at that in a second. But with powers of 10, you have a good chance you'll see it as a decimal. So recognizing our powers of 10, we're using a decimal. So this is 1 0 after the decimal point. I mean, this is just the first point is one spot after the decimal point. This is going to be where the 1 occurs 2 spots after the decimal spot, 3 spots after the decimal spot, and then 4 spots after the decimal spot. Now, if you add the 0 in there, it can tell you how many zeros you have. Do 0 point, and then that tells you how many zeros you have also, if you lead it with a 0. But just think about moving it over the decimal spot that many times in terms of getting the number. So you just kind of want to be able to recognize those forms. Okay, next thing you need to know is your rules. The most common one you're going to use is this one. If you take an exponential and you raise it to a power, we multiply our exponents. So here's an example. We have 3 to the 4th raised to the x plus 1. That becomes 3 raised to the 4 times x plus 1. I could rewrite that as 3 raised to the 4x plus 4. Another one we'll be using, we have b to the x times b to the y. Now b to the x times b to the y, we add our exponents. So that's b to the x plus y. So you might have something like this, 2 to the 5th times 2 to the x plus 1, that becomes 2 to the x plus 6. Recognize that when you do 1 over b to the x, it's the same as writing b to the negative x. We want to get everything on the same level. So I'm going to kind of combine these two steps, the one we just did, and looking at an example here. So let's say we had 1 over 5 squared times 5 to the x plus 1. I rewrite 1 over 5 squared to 5 to the negative 2. and then I can add my exponents. So negative 2 plus x plus 1 gives me 5 raised to the x minus 1. Last one we want to look at is taking a radical, some kind of a square root, or taking any kind of an nth root or eighth root. When you do this one, the format is b raised to the x over a. So let's say we had the cube root of 7 raised to the x minus 1. That's 7 raised to the x minus 1 over 3. Now be careful. If you just see a square root, remember the index that's over here is a 2. So let's say I had the square root of 10 to the x. This is going to be 10 raised to the x over 2. The idea is we want to break these down to their smallest base. Okay, so basically what we're going to do is we're going to try to match bases to solve. So this first example is a real simple one. It doesn't have too much going on with it. I got 1/3. This is the same thing as saying 1 over 3 to the first. So this becomes 3 to the negative 1. 27 is 3 cubed. So I get 3 to the negative 1 equals 3 to the 3x. Once my bases match and I've got nothing else going on with it, if this is true, the bases match, then the exponents must match. So I get negative 1 equals 3x. Divide by 3, I get negative 1/3. Okay, a little more complicated example, but still not terrible. I'm going to change each of these to powers of 2. So 8 is 2 to the 3rd. I've already got a power of 2 here. 32 is 2 to the 5th. So I get 2 to the 3rd times 2 to the 2x, 2 to the 5th, raised to the 4x minus 3. So I multiply my exponents. And then these guys are going to put together. So I get 2 raised to 2x plus 3. You may have decided to distribute this one through at that point, made that 20x minus 15. That's fine. But once I get the bases match, I can drop the bases and set the exponents equal to each other. Now it's a question of solving just like normal. So I got 20x minus 15. Subtract 2x. I got 18x on the right side. Add 15 to the other side. I get 18. So I get 18 equals 18x. So x equals 1. Okay, one's a little more complicated. Again, I want to change these all to the same base. In this case, I'm going to use a base of 5. So 1 over 5 to the first. 25 I could change to 5 squared. So 1 over 5 to the first is 5 to the negative 1. This becomes 5 squared raised to the 2x minus 3. So I'll get 2 times 2x minus 3. And this one gives us our fraction. This would be 5 raised to the x over 3. Got to put these two together. So if you wanted to, you can do 4x minus 6 and then minus 1, make it 4x minus 7 right now. Or you could wait till after you go to solve it. But once I get the bases matched with nothing else going on, say I have bases matched, but I've got extra pieces. I got to get them all into one base on one side, one base on the other that match. Okay, you can drop it off, and now I'm just going to simplify. So I get 4x minus 6 minus 1. So I get 4x minus 7. I'm going to multiply both sides by 3. We get 12x minus 21 equals x. So I'll get 11x equals 21. Let's move the 21 to that side, subtracted x. And then divide by 11. I get 21 elevenths. Okay, so once you get done matching your bases, it's just doing algebra. Okay, let's look at one more example. So this one looks pretty nasty. So we're going to go through all the steps right here because it's got everything going on with it. First, we'll work with powers of 3. 81 is 3 to the 4th. 9 is 3 squared, so this would be 3 to the negative 2. 3 here, well, that's just 3 to the 1st. 27 is 3 cubed. So my next step, this is going to be 3 raised to the 4 times x plus 2. This is 3 to the negative 6th. This right here, I get 3 to the 6th, I get 6/7. Now I've got to get my bases to be all together. So I get 3 to the 4x plus 8 minus 6. This one, 3 to the first, I get 1 plus 6/7. What? 7/7 plus 6/7, that's 13/7. So I got 4x plus 8 minus 6, and now it's going to equal 13/7. So that's 4x plus 2 equals 13/7. Multiply by 7. Get 28x plus 14 equals 13. We'll subtract 1, and then divide by 28.